Well, math is very much a part of architecture every day.
Wrapping my head around concepts of the experience of geometry, or a feeling of space given by a thicker wall versus a thinner wall, or the way a window goes through the wall. A lot of this was a completely new language the first time I heard it.
So you start with the question and the problem, and you work your way back to what kind of math and science will help us solve this problem.
We use an enormous amount of geometry, trigonometry, algebra to figure out ratios of one wall surface, say, to another wall surface.
Architecture for centuries has been engaged with the study of proportional systems. Any student coming into our program would certainly be expected to be very comfortable with trigonometry.
Trigonometry is absolutely head-bangingly essential, unbelievably essential. I have used it every day for the past 6 months.
In a basic structures class or a construction class or an environmental technology class, all of which would use trigonometry at some points.
Of course, it comes into play with dimensions.
That triangular shape is really important in structures, and we use those to calculate the sides of triangles in relationship to the angles of the triangles. Anytime you draw a sloped roof, you have to start to incorporate trigonometry.
You can take a really simple problem like a house or a picnic shelter. There are several factors to consider. A lower angle involves less material. How do I know that? We got to calculate that. And the steeper we get, the better it sheds rain and snow and ice and all those things. So how do we figure out what exact angle we want on that roof? Then we have to know this length, and then from that, using trig, we can calculate the angle and know whether or not we can walk on it, whether or not we can use shingles or slate or clay tiles or a flat surface rolled roof. All is determined by that angle.
We have to know how to calculate the lengths of those triangles and those angles. You could look at this system starting to take over the structural definition of that space. Yeah.
And then we tilt the roof like this. Well, how high do we make this piece right here? So we've got to figure that out if we want to know what the length is. Start with conceptual ideas. What do you want it to look like? What do you want it to do? And then you start to talk about how big is it and how do we measure that?
We were building a 13-story addition to a hospital here in the Cincinnati area, and the exterior wall was made in precast panels, and they're actually prefabricated off-site and brought to the site and put on the side of the building. So when you make these things, you got to make sure they're going to work, because when they show up, that's what you have.
You can calculate how deep you would need an overhang. And then as a designer, if you want to sort of take that step, we say, well, what do we want it to look like? and how is that pitch going to impact that? And it's this sort of balance between the limiting factors and the design intent, and we have to use trigonometry to come up with a solution.
And you start getting into this sort of bridge between art and science, where you start talking about what sort of sensations or experiences different geometries create.
It's critical that we take the time to work through the problems so that we develop an intuitive understanding of those relationships also. And that only comes from taking the time to actually work through the equations.
And they measure it, they draw it, use scale. The idea of scale is really important. So how do I take something that's this big but draw it on a piece of paper that's this big?
If you just plug numbers into a computer, it can provide an answer, but we don't actually understand how we got to that answer.
It's about responding to exterior things. So sometimes you're given variables that are kind of outside of your own hand, and you have to respond to those variables, and you have to use math to figure out what the missing piece is.